We're now looking at exam questions regarding situations with friction. The first question is this one, question 5. This is from winter 2011, paper 41. And you have these two diagrams, and then it says that a block of mass 2 kilograms is at rest on a horizontal floor. The coefficient of friction between the block and the floor is mu. A force of magnitude 12 newtons acts on a block at an angle of alpha to the horizontal, where tan of alpha equals 3/4. When the applied force acts downwards, as in picture 1, the block remains at rest. Show that mu is bigger or equal to 6/17. Okay, I mentioned this before on a previous lesson. I don't like when the forces are represented on objects such as the way over here. I like to put all forces acting on a single point. I like to treat objects as a point mass. All situations, all questions in Mechanics 1, you may think of objects as point masses. I still want to represent the object as with a certain shape. It's more relatable to real life, but I put all forces applied on its center. So that's what you're going to see. Let me put it on the right place. It's this one. Okay, so on question 1, the situation that you have is basically this. You have this force, which I'm now representing, applied in its center. What else do I have? I have the weight pointing down. I have the normal contact force pointing up. And if this object is under this force, the friction is going to be pointing to the left. Don't forget that this force is trying to make the object move to the right. Friction always counters motion, so in this particular case, it's going to point to the left. So the 1, 2, 3, 4 forces applied to the object are these. In this case, the referential that you would use, it's very simple to select. It's basically horizontal, vertical, x, y, which means that the 12 Newton force is the only one to be decomposed. This angle alpha over here will now be over here. So the horizontal component of the 12 Newton force is 12 cosine of alpha. This is the adjacent to this triangle. This over here, the vertical component is that side, so it's 12 sine of alpha. All right? If this is on the verge of moving, then the circumstances that you would have would be these, okay? The 12 cosine of alpha, the only force pointing to the right, needs to be equal to the only force pointing to the left. And vertically speaking, the 12 sine of alpha plus the weight, these two forces pointing down, equal the only force pointing up. All right? Now, what is the thing about the friction? The friction is a force that can vary until a maximum value. What do I mean with this? I told this in lesson. If this force that is trying to push the object to the right increases, but the object is not moving, the reason for it not to move is because the friction pointing in the opposite direction is going to be the same size. If it is now a little bit bigger, this is also going to be bigger. But this doesn't get bigger forever. It's going to be a limit starting from which this force is going to be bigger than the friction and it will accelerate to the right. All right? So it makes sense to represent the coefficient of friction. Don't forget that friction equals the coefficient of friction times the normal contact force. And this one stays the same. So the coefficient of friction is going to be bigger or equal to a certain value. Under the circumstances that the question is talking about, if the coefficient of friction gets below or would be below a certain value, then this force will be enough for this to move. Okay, so let's translate this into math. So horizontally speaking, that's what you have. Vertically speaking, this is what you have. And now let's just solve it. As I told you, friction is the coefficient of friction times the normal contact force. So the coefficient of friction is going to be 12 cosine of alpha divided by n, but n is this, so this is the expression. You now just have to substitute by the values. You get the 16 over 17, and any value of mu smaller than this would make the block move, so the mu must be bigger or equal to 6 over 17. Okay? When the applied force acts upwards, like in this picture, the block slides along the floor. It's still the same 12 Newton force. The angle is also the same. It's just the direction that is changing. So what is going to be the circumstance right now? Again, I'm applying this at the center. I'm still decomposing the 12 Newton force. All the other three stays the same. Okay? So now you know that it will move. The question is telling you that. That. Okay? So you need to figure out another inequality for mu. In order for this to happen, sorry, let me go another way. Let me just do the representation of forces and then I'll deal with that at the end. So I have the 12 Newton force decomposed pretty much the same way as before. Okay, horizontal component is 12 cosine of the angle alpha, vertical is 12 sine of the angle alpha. Horizontally speaking, in order for this to move, this force needs to be bigger than the friction. Okay, and vertically speaking, the sum of these two forces needs to be equal to the weight. Okay, so I solve this in terms of n because I'm going to need it for the friction. The friction is mu n. Okay, so now this is already an inequality, and this is what you want. I can have this expression over here, which I then can substitute by the corresponding values, and I have this, and this is what the question is asking again, is an inequality for mu. There you have it. Mu needs to be smaller than 3/4. Otherwise, the 12 Newton force won't be enough to make it move. All right? Make sense? Next one. Winter 2014, question paper 41, question 5. A small block B of mass 0.25 kilograms is attached to the midpoint of a light inextensible string. Particles P and Q of masses 0.2 and 0.3 kilograms respectively are attached to the ends of the string. The string passes over two smooth pulleys fixed at opposite sides of a rough table, with B resting in limiting equilibrium on the table between the pulleys, and the particles P and Q and block B are in the same vertical plane. Find a coefficient of friction between B and the table. So it's a rough table. You have here B resting in limiting equilibrium, so is on the verge of moving, is at a maximum friction, okay? And you need to find a coefficient of friction. So let's just represent the forces in the diagram, okay? Particle P, the whole thing is still in equilibrium, so the weight equals the tension 1. By the way, you have two tensions because you have two strings. You have T1 and T2, okay? Same situation for question mass Q. And here what do you have? You will have, pointing to the left, a force, a tension with magnitude equal to that one. To the right, you have a tension with magnitude equal to that one. You will also have force up, the normal contact force, and a force down, the weight. These two need to be the same. They are the only forces that are vertical that you have on object P. And now you have a friction, and you have to decide the direction of the friction. And this one's easy. You just look at the masses. B, which one is B? Okay, I think it's this one, B and P. Let me look at the question again. P and Q, okay. I called something different. P and Q. P, this is supposed to be Q. Okay, the mass of Q is slightly bigger than the mass of P. So With no friction, the whole thing would move that way, kind of clockwise, right? Since you have friction and you know that this is not moving, the friction must be opposite to this attempt of motion. All right, it's pointing to the left here on B. Did you understand how to get the direction of the friction? It always counts motion or the attempt of things to move. So in this case, it's going to point to the left because B tends to go to the right because this is heavier than that. All right? Okay, so let's put all this diagram and translate it into mathematical equations. For P, what you have, T1 equals the weight of P. So T1 equals basically 2 newtons. For Q, the same thing. T2 equals the weight of mass Q, which is 3 newtons. And for B, well, in X, you have T2 equals T1 plus friction. And on Y, you have the normal contact force equals the weight. All right? So the normal contact force equals the weight of mass B, which is 0.25 times 10, so 2.5. All right? And the friction is going to be equal to T2 minus T1. T2 is 3, T1 is 2. This is supposed to be 2, okay? 3 minus 2, which is 1, over the value of n, which is 2.5. I'm going to pause here just to make this correction before I forget. Okay, as you can see, magically changed into a 2, so now it's correct. So basically the value of mu is 0.4. It continues. Q is now removed so that P and B begin to move. Find the acceleration of P and the tension in the part PB of the string. All right, so now that you do not have Q anymore, what do you have? You have this moving, so this means that on P, the weight must be bigger than the tension. And on object B, the tension must be bigger than the friction. Notice now that the friction is pointing the opposite direction. Okay, and what value is it going to be? It's going to be the maximum value, which is going to be n times the coefficient of friction that you got a little while ago. All right? Notice also that since you only have one string, this tension has the same magnitude as that one. So on P, you have its weight minus the tension equals the mass of P times the acceleration. The acceleration is the same on these, right? So basically, this is what you get. You have this equation. For B, you have first on the horizontal axis, you have the tension minus the friction equals the mass of B times the acceleration. Notice that either side, that positive is everything that has this overall direction. So this force would be positive, this force would be positive, this force would be negative, this force would be negative. Okay? On Y, you have here n equals the weight of B. Okay, so n equals 2.5 again. The tension minus the mu, which we just calculated, is 0.4 times the n, which is 2.5, equals the mass of B, 0.25 times A. So you have two unknowns and two equations. It's just a matter of solving them using simultaneous equations. Okay? And by doing that, you get both the values of T and A. Question solved. Let's look at still another one. Question 4 on a winter 2015 paper, paper 41. You have this diagram, and then it says that blocks P and Q of mass m kilograms and 5 kilograms respectively are attached to the ends of a light and extensible string. The string passes over a small smooth pulley which is fixed at the top of a rough plane inclined at 35 degrees to the horizontal. Block P is at rest on the plane, and block Q hangs vertically below the pulley, as you can see in the diagram. The coefficient of friction between block P and the plane is 0.2. Find the set of values of m for which the blocks remain at rest. Okay, this is a slightly different question. Now, what is the thing that can change? It's Q. If the mass of Q can change, the circumstances of the diagram of the what is being represented is going to change. If you think a little bit, you will realize that if this mass is too low, what is going to happen? The whole thing is going to start moving in that direction. P goes down, Q goes up. But if the mass of Q is too big, then what will happen? This will go down and this will go up. What is keeping this in place is the friction. In the first situation that I told you, the friction points up the plane because the whole set tends to move down the plane, or particularly block P tends to move down the plane, so the friction points up. In the second situation, when Q is too big, now block P tends to go up, so the friction will point down. Okay, so this is the circumstance that is going to define the range of values that Q can have so that P stays in place. Make sense? So let's go over here. Let's start with M being too low. When M is too low, the whole thing is in equilibrium still, all right? So you have the tension over here being the same as the weight of Q, whatever it is. This tension is the same as that one. This part is always the same. You have here the weight. In this case, the weight is a small vector. The friction in this case points down the plane because the block P tends to go up the plane. No, let me think again. Okay, I just spotted a mistake that I told you at the beginning. The concept of the question is the same. I just misunderstood which mass is changing. The mass that is 5 kilograms is Q. This is 5 kilograms. This is the one that will change. Everything that I said is the same, but this is the mass that is changing. If this is too big, the whole set will go down the plane and the friction points up. If this is too small, then the whole set tries to go up and the friction points down. Okay? But the reasoning behind the question is still the same. All right. Sorry about that. Now that I have this corrected, now if M is too low, M again is the mass of this 5 kilogram mass will be enough to push this up, right? So in that case, the friction is going to be down, pointing down, all right? So in relation to block Q, you have the weight equaling the tension, or the tension equals the weight, doesn't matter, all right? You know the weight over here is 5 kilograms, so you know the value of this tension is 50 newtons. This tension is the same as that, after all, is the same string. So now that I have this represented, again, the weight is decomposed already on its horizontal and vertical components. So on X over here, what do I have? I have the tension equals the horizontal component of the weight plus the friction. On the vertical side of the referential, I have the normal contact force equals the vertical component of the weight, which is Fg cosine of 35. What is friction? Friction equals mu times n, all right? And n, I just got the value over there. So I can put everything as a single equation, okay? I'm just factorizing mg over here. And m is basically the only thing that I'm missing. I'm just substituting by the values and doing the algebraic manipulation. And here we have the mass of the object, okay? The lower that it can be. Now let's put this bigger, all right? So as you can see, the weight changed from being this arrow to this arrow, okay? So this will increase both the horizontal component and the vertical component of the weight. As a consequence, the normal contact force will also increase, and as a consequence, the value of the friction will also increase, right? Now, this tends to go down, so the friction is now going to point up. So the distribution of forces is going to be slightly different. Not in Q though, in Q is still the same, right? But now the friction points up. So horizontally speaking, you have the horizontal component of the weight equals the tension plus the friction. The vertical component, the relationship is the same, okay? Now I just plug this over there. Again, I have a single equation. My only unknown is m, just like before. I substitute everything, I do the algebraic manipulation, and I get this value for the new m, 12.2 kilograms. So this is the maximum value of m, and this is the minimum value of m for which the block is going to be, or the system is going to be in equilibrium. That's what I have over here.